All right, so this is the second segment of section 7.4. Recall we were talking about sort of graphical representations of vectors and looked at ways to multiply them by scalars in a way that made geometric sense, and then also add them, and came up with an important result that the addition of arrow vectors is a commutative process, just based on the way that, that we've done this. Now, I'm not going to exactly follow the process that's laid out in the book, because usually this segment, when I do this in a classroom setting, is very abbreviated. I want to get you down to the point where you can represent these things and be able to work with them, to actually do something with them, rather than spend a lot of time on all this kind of theoretical stuff and everything else. So if you want, go back and read through the book on these bits about calculating the magnitudes of you know, the resultant and all that sort of. The resultant is what they describe when you add two vectors together. The equals is what they call the resultant. Not terminology I'm going to be too worried about. But what the task that we want to do is we want to be able to take different representations of vectors. Like currently we've talked about what's this magnitude direction, which the graph is related to that, right? You have a length and a direction, magnitude direction of an arrow, and we'd like to look at what's called a Cartesian or standard form, sometimes called component form. All those words are interchangeable. So without further ado, let me get over here, and I want to give you some notation that I'm comfortable using that is relatively standard throughout the mathematics world. Now, when you go and do this in a physics class, they're going to give you totally different representations, which is just so convenient. Every science wants to do things slightly differently. So we have section 7.4. I think we're now on page 3. So consider a vector. Let's just, again, just kind of pull out a vector U and have it here as reference. We're not going to do much more with the geometry of this, but so we could talk about once we put a coordinate system in place. So put this arrow into a universe somehow. Once we do that, we establish a couple quantities. So let me try to just pretend like, here we go. Here's this coordinate system that we put in place. It needs to be an orthogonal coordinate system, but it doesn't have to necessarily be horizontal and vertical. Right, so here maybe we have x and y. If this was a vector related to displacement, like moving from point A to point B, what we have almost immediately is something that looks an awful lot like an angle, and that's kind of intentional. Notice that there will be some angle associated with this, the same way that we've measured angles previously. There will be some kind of theta. And to distinguish it from other angles, which we might be working with multiple vectors, we put a little subscript on it, u. And then, of course, the length of this is related to, if you think about when we first defined the trigonometric functions, we said, well, to a point on an array that has certain properties, here's its x-coordinate and y-coordinate, you can think of this tip of this arrow as being that point. So what we'd like to make the association with is that the length of this arrow is given a symbol that represents its magnitude. So I'm going to use this one. It's kind of the absolute value sign of a vector. So in mathematics, you see that we often just recycle symbols. But this one, in this context, when you have this absolute value symbol with a vector sandwich between it, is not called the absolute value. It's actually called the magnitude. So let me kind of, and that doesn't change based on the coordinate system. So let me give a little bit of definition here. So U, or notation. So this represents the length, and I'll use that in parentheses because it's not necessarily a length of the arrow. Sometimes, it's pretty universally called the magnitude. Okay, got an extra I in there, but I think you get it. So called the magnitude. And theta sub u, this represents the direction of the arrow. And rather than get long-winded here, it doesn't necessarily have to be the case that the origin coincides with the tail of the vector. It's really more about with reference to the x direction, if you will, not necessarily the x-axis. Because we could have these vectors in different space. You know, typically you're not working from the origin all the time, or if you start talking about adding two things up, you have to have a context of what it means by direction. But I think that's a pretty easy concept to understand if you want to think about it in terms of like north, south, east, west. Even though you might not be standing on the equator, figuring out which direction north, south, east, west is not a challenging sort of exercise. That's a little, depends on how accurate you want to be, but the concept is not difficult. So the thing that I want to point out here, though, is that this direction is entirely dependent on choice of coordinates or choice of coordinate system. So if you want to rotate your physical space, and use a different set of coordinates, we don't want to end up with mathematics that works differently depending on whether you pick up is left or right is down or whatever else. And it turns out that we won't have that problem. It's just that you have to understand that first, in any sort of representation that has magnitude and direction, you have to select a coordinate system first. Now, we're also going to talk about some quantities that are, so these are the magnitude and direction. We're also going to use some symbols that are used, and maybe I'll just kind of draw this picture again, or maybe just add some extra bits to it. I'll just draw it again. So here's our vector u again. And here's our coordinate system for it. Now this is an angle in quadrant 1. I mean, we could put this in quadrant 2 or any other place that we want. It would be just fine. Just like we had before when we were defining these trig functions, remember this absolute value of u in some sense is representing the r value that we had. We have sort of some other corresponding bits here, which we will call this u sub x and u sub y. You can read those as the kind of the x coordinate of u and the x and the y coordinate of u, if that seems like an appropriate way to talk about it. But the way that we represent the vectors, so u sub x, this is the component of u that lies in the x direction and I'll put in here, it is not a vector. So this is just a scalar. But when we talk about the x direction, what would make sense is to create maybe a vector that has a unit length in that direction, and then this vector from, as maybe you can see here, if you were to talk about just this vector, right, that would be sort of a lead in to, well, if I added this vector to maybe say this vector, then I get u back, right? So that the idea then is that maybe I can represent these in a couple different ways, but I would need to come up with sort of a unit vector in this direction. And so I'm going to go ahead and do that right now. I'll use the letter I with this funny looking hat on top of it, and I'll call this so is, now again, these are based on the coordinate system that you select. So I hat is a unit vector, meaning it has a length of 1 and no variables attached to it. So I is a unit vector in the x direction. Now we could say all of the same things about the other piece of this. We could repeat all of that same wording, except we're going to change x direction to y direction. And we're going to use a different symbol for a unit vector in the x direction. So I will just simply say u sub y component y direction. And j hat unit vector y direction. Okay? So there's also, for three-dimensional work, you move into what's called, well, as you can imagine, you might have a u sub z, and then you use a k for k hat for a unit vector in the z direction. It turns out that there's a very famous mathematician and physicist from the early 19th century by the name of Hamilton that did a lot of work with what are called quaternions. It's just, sort of like the next higher level of numbers beyond complex numbers. And so the similarity of these two, like what you think of as the imaginary number, is not really an accident. It's there on purpose. And if we had time to go into chapter 8, I might even begin to show you where some of that comes from. But we don't, we have to pick and choose as to what we're going to do. Okay, so now that we have sort of all these definitions of different symbols, remember, all of this requires that you first select a coordinate axis of some kind. And if you don't have a coordinate axis, the only thing that really still exists without a specific coordinate system is the length of this arrow. It doesn't define the direction, doesn't define these components, it doesn't define the unit vectors, anything. So you have to start by picking a coordinate system. Remember, that's what we did with our, when we first started looking at angles in a trigonometric context. So it's very similar development. All right, so let's look at these different sort of representations. And some of these may be a little bit different than the way the book uses, because I sometimes think that the book's just a tad bit primitive. And again, I'm not going to go into all of this mathematical development, because all I really want to do is to get you to the point where you can convert between the two, and you can add them, and you can do maybe some interesting. There is an interesting result which involves the law of cosines that we'll look at. I think that's in chapter 7.4 or 7.5. Okay, so first let's look at the two different representations. We have the magnitude direction representation. So u equal to, and I'm going to use a parentheses, magnitude u, comma, theta sub u. Okay, now this is a two-dimensional vector, so this theta is understood. Right? This would be in what we would call a polar coordinate system. Magnitude and direction. So this is easily, now why is this important? Well, when you actually measure things, like it's much easier to talk about what their magnitude is and what direction they're headed than it is to talk about their components, because the components are could be a little bit harder to measure and require indirect measurements of these things to begin with. So you wouldn't be able to just go straight with components. Maybe from a mathematical sense you could, but not from a physical sense. So usually this is the kind of thing you start with, is a polar coordinate or a polar magnitude and direction. You do some calculations using these other versions, and then you come back and convert them back to this. So that's kind of what one of our tasks are. So here's the polar representation, polar coordinates. If you want to do this in with magnitude and direction, it's u sub x times I hat plus u sub y times j hat. This is one way to represent this. This is what's called there are different ways of, there are different terms that are used, but standard form, Cartesian, component, and these are usually followed by the word form or form is pretty standard, but or you could think in terms of coordinate as well, but then any of those terms, when you see these, this is representing sort of an x and a y, which implies some kind of a coordinate system has already been laid on there. Now this is kind of superfluous notation. Yes, it's very explicit. And notice these are real numbers, right? They're multiplication of scalars by a vector, but it's kind of cumbersome because you have to write all this stuff and it's the same every time. So there's the shorthand for this is to use these brackets, sort of angled parentheses, and just list the individual real numbers that are associated with them. So this is two different representations of the same sort of thing. Now, if you look at the way that Euclidean geometry works, addition of these vectors, if you had, say, a u and a v, is much, much easier in this form because we just simply add things up by their components and then spit out another component, which is kind of a nice little deal. So let's maybe talk about addition of vectors and sort of see why that's preferential in this form as opposed to this other one. And I'll just kind of do that very quickly and then we'll end this video. So suppose you have two vectors. Let's say u, which equals ux, uy, and v, which equals vx and vy. Find, let's say u plus v. So in vector form, find what it equals, what its components are. Well, okay, so let's think about this. So first off, we can write u plus v as being equal to uxi plus vxi plus uyj plus vyj. I kind of mixed them up here. U is ux plus uy times their respective direction vectors, and then v is vx plus vy times their respective direction vectors. But notice I'm just doing that to pair them up. So here we have that this is ux plus vx times I hat plus uy plus vy times j hat, which just happens to be represented as ux plus vx, comma, uy plus vy. Really simple application with just symbols alone, but what if we have it with some numbers? Let's say u equal to 2 comma 3 and v equal to 1 comma negative 1. So to get the sum, you just simply add the first numbers together and you add the second numbers together. You end up with, this is pretty trivial, 3 comma 2, right? And then you could find, this would be much easier to represent this without actually drawing any pictures or drawing any arrows. Okay, so that's the end of segment 2. I'm going to come back and maybe do this with some components, some scalar multiplication first, and then kind of show how you would do, like, say, I don't know, 2u minus 3y or something, whatever. We'll look at some other things. Then we're going to talk about the conversion. So that'll take a little bit of time to develop, but I will see you here very shortly.